A price chart, volatility estimate, and risk report should not disagree because one candle contains impossible geometry. Yet a bar can look ordinary while its high sits below its open, or its low sits above its close. If that row travels downstream, the defect becomes harder to trace. An OHLCV consistency check catches the contradiction at ingestion before it reaches analytics. The practitioner gets a series that is safer to interpret. The builder gets exact reasons, the untouched source row, and evidence that can be reproduced without silently inventing a repair. We will define OHLCV in plain language, build the 3 price containment rules, convert tick tolerance into price units, and test the exact equality boundary. Then we will separate malformed fields from impossible geometry, implement the same contract in Python and TypeScript, and verify their ordered results with shared fixtures. Candle anatomy supplies the geometric vocabulary. Time bars explains how trades become one interval. Here, the job is narrower. Decide whether one reported bar satisfies its declared structural contract, preserve every issue, and keep detection separate from diagnosis or repair. OHLCV summarizes one instrument over one declared interval. Open is the first qualifying price. High is the highest. Low is the lowest. Close is the final qualifying price, and volume measures the source-defined activity in that interval. The exact definitions depend on the product, so pin the instrument, venue, session, currency, stored scale, adjusted or unadjusted basis, qualifying trade policy, tick table, and source version before comparing anything. All 4 prices must share that basis. Mixing cents with dollars, adjusted with unadjusted values, or different venue scopes can manufacture an alert even when each field was valid in its own context. Let O, H, L, and C be normalized prices. Let epsilon be the allowed tolerance in price units. Rule 1 says high plus epsilon must be at least low. This prevents an inverted range. Rule 2 says high plus epsilon must reach the larger of open and close. High must contain both ends of the candle body. Rule 3 says low minus epsilon must be no greater than the smaller of open and close. Low must contain both body endpoints from below. Equality passes in every rule. Volume is part of OHLCV, but it has no place in these 3 geometry inequalities. It receives its own field validation. Tolerance should describe a source convention, not hide a bad row. Let tick size Q equal 1 cent and tolerance an equal 1 tick. Epsilon is Q times N, so the comparison allowance is exactly 1 cent. Now set open to $100 and 1 cent, high to $100, low to $99.50, and close to $99.90. High misses the body maximum by exactly 1 cent, so equality makes the bar pass. Change only open to 100.0101. The miss becomes 1.01 cents just beyond tolerance, and the result is high below body. A tiny machine round off guard protects the exact boundary. It is not extra business tolerance. With 0 tolerance, set open to 102, high to 101, low to 103, and close to 102. The range is inverted by 2. High is below the body by 1. Low is above the body by 1. The useful result is the complete ordered list. High below low, high below body, and low above body. Stopping after the first issue throws away diagnostic evidence. Changing high to 103 or low to 101 could make the geometry pass, but either edit invents a value unless an independent repair process has stronger source evidence. Some feeds store $100.01 as integer 10,001. A declared price scale of 0.01 converts every price into the same normalized unit before the rules run. Tick size must use that unit too. But one scale cannot repair a row where only some fields are in cents. Field validation comes first. All 4 prices must be finite numbers. Missing values, booleans, numeric strings, nan, and infinities receive field-specific issues. Geometry runs only when every required price is valid. The timestamp must include Z or an explicit UTC offset. Optional volume may be 0, but it cannot be non-finite or negative. Strict ordering prevents coercion from disguising a broken source contract. The validator answers one question. Does this row disagree with the declared contract? It does not decide that a vendor was wrong, reconstruct a replacement price, or certify that a passing row is economically correct. Possible causes include a wrong decimal scale, a missing marker parsed as 0, mixed adjustment bases, different venue scopes, a time zone join error, a stale partial update, or an upstream publication defect. The last cause is only one candidate. Preserve the raw row, source, ingestion time, schema version, adjustment version, and validator version. Quarantine the record while the evidence is investigated. Repair belongs downstream and requires independent, authoritative correction evidence plus a versioned approval policy. The implementation stays small because the contract already made the hard decisions. First, validate tick size, tolerance ticks, and price scale. For each row, shallow copy the raw mapping and selected provenance. Validate timestamp, prices, and optional volume without coercion. Normalize finite prices with a 1 declared scale. If all 4 normalized prices exist, calculate every geometric gap and append each issue in canonical order. Finally, emit an immutable diagnostic containing index, timestamp, validity, ordered issues, effective tolerance, normalized prices when available, provenance, and the untouched raw row. Python and TypeScript follow this same sequence. The output is an audit record, not a clean replacement bar. The shared fixture fixes the equality policy, issue ordering, malformed input behavior, and provenance output for both languages. Tests cover a clean bar, every geometry issue combination, exact 1 tick equality, the first value beyond it, scaled integer prices, missing and non-finite fields, invalid timestamps, 0 and negative volume, invalid configuration, and raw row preservation. A deterministic 120-bar synthetic corpus adds broader coverage. Matching results prove conformance to this package and Python TypeScript parity. They do not prove that the configured tick size is historically correct, that a passing row contains every qualifying trade, or that any trading decision will be useful. The interactive playground turns the contract into a console. Start with the canonical mix to compare clean bars, high failures, low failures, inverted ranges, and volume errors. Switch to the 1-tick boundary to see exact equality beside the first value beyond tolerance. Then open malformed input to inspect missing, string, non-finite, and invalid timestamp cases. Change tolerance in ticks and watch the candle, current rule, issue list, normalized values, raw row, provenance, and audit window recompute together. Back, step, play, pause, and reset make the sequence inspectable, and reset always returns to the same deterministic state. A passing bar can still be stale, incomplete, assigned to the wrong session, or built from the wrong adjustment basis. Overbroad tolerance can hide a repeatable parsing defect. A current tick table may be wrong for the instrument's historical price band. Geometry cannot detect duplicates, missing intervals, calendar violations, corporate action basis mismatches, source disagreement, or local outliers. Run this validator early, preserve its audit record, and continue with those independent controls. You can now define the 3 OHLC rules, handle exact tick boundaries, report every field and geometry issue, and keep detection separate from repair. Next, Hample bad tick filter finds prices that are internally possible but locally implausible. Continue with the full OHLC consistency validator article, source code, tests, and playground on the fintechbuilder.com.